Okay, good morning everybody. I did say last week that Neil was supposed to be lecturing. He can't do it today because his partner's father has died and so they've had to go to the funeral. So you've got me today, I'm afraid, but you'll have Neil next week talking about the next steps. But today we're making a shift from what we've done previously. We're going to start looking at what's called frequency response. Bode plots and Nyquist diagrams. So, what is frequency response? We'll cover that first. Frequency response produces two numbers that we use to talk about frequency response. Those are called amplitude ratio and phase. And you can analyze systems using frequency response with these two things called a Bode plot or a Nyquist diagram. And they're basically representations of these two, amplitude ratio and phase angle. And then the last thing we're going to do today is system identification. We've got quite a lot to cover today. Hopefully I'll get through it all, but if not, it'll be worth your while possibly watching the video online because I'm going to go through stuff quite quickly. But also you can download these notes and there's some extra notes on Blackboard as well, a handout with some more information about this. So it's worth your while to visit Blackboard and take a look at this stuff. But like I said, hopefully I'll get through it all today. Fingers crossed. So, frequency response. Well, up to now we've been looking at time response. So this is how a system behaves as time increases from 0 to infinity. Okay, and so the system behaves to a specific input with respect to time. Frequency response is different. Okay, we look at the system now, but instead of looking at how the system behaves with respect to time, we look at it in response to a sinusoidal input. Okay, and that sinusoidal input will obviously be at a certain frequency, and we look at, instead of it just over a single frequency, we look at it over a range of frequencies. And so, you know, in radians per second, we could start at, say, 0.01 radians per second and go up to 10 radians per second. And we look at every frequency. So frequency response, we can use it to identify systems, which we'll talk about in a minute. When say you've got a real system, if you do frequency response analysis, you end up with a plot, a Bode plot or a Nyquist diagram, and from that you can then identify what the transfer function of that system is based on the plot. Okay. The other thing you can use it for is what's called stability analysis to know whether the system's going to go unstable, and that's what Neil is going to talk about next week. So, frequency response, system behavior determined from the steady state response to a sinusoidal input in the form, obviously this is a sine function. R is some amplitude multiplied by the sine of omega t, omega being the driving frequency in this case. And the sine wave is used because it's easy to analyze, it's easy to generate, and if we take a system and measure it experimentally, it's easy to measure. Okay, that's why we use a sine wave. Equally, you could use a cosine wave. They're both sinusoidal inputs. In this case, we're going to use a sine wave. And so, you apply the sinusoid to any linear system, okay, and there's a few things that will happen. Firstly, your output will be sinusoidal. So you've got a linear system. If you put an input, the output's going to also be sinusoidal. The amplitude of the sinusoid will be proportional to the input amplitude. If you double the input amplitude, you double the output amplitude, okay? And you've entered the sinusoid with a specific frequency, harmonic frequency. And if that frequency is, say, 10 hertz, the output frequency will be the same, 10 hertz, okay? So there's a few things that we know about linear systems. But there will be a variation in amplitude. There tends to be a variation in amplitude and also phase, okay? And that will depend upon the frequency that you're applying. And so let's look at an example. This is just looking in the time. We've got a sum function, g of s, some transfer function, g of s. There's our input, a sine omega t. And we get, this is the input, okay? So a nice sinusoid curve between 0 and 20 seconds. And then we have an output. The output is the green line. And notice that the whole thing is, there's a lag between the input and the output, okay? And there's a difference in amplitude. But the frequency is the same. 1 period for the sine comes up to there. 1 period for the the output comes up to there. So the frequency is exactly the same. Periods are the same. And so I talked about things like amplitude ratio and phase. Well, that's the amplitude of our input frequency, A, okay? And the amplitude of our output frequency is B. So the amplitude ratio is obviously the ratio of those two things together, B divided by A. And that's dimensionless. Obviously, if this is measuring meters, then obviously that's meters divided by meters, which is dimensionless. So that's the amplitude ratio. Then we look at the phase. Okay, well, 1 period of the input oscillation is going to be obviously from, as this is crossing 0 here, and this is crossing here, that's 360 degrees. That's 1 period. Okay. The phase looks at the difference between the two traces, the input and the output. And so that is going to be the phase, and that's represented by the Greek letter phi, and that's also measured in degrees. So if this is 360 degrees, then obviously this is going to be, 15 degrees or 20 degrees, something like that. But because it's I'll talk about that in a second. That's called phase shift. It's an angle represented in degrees by the Greek letter phi. That's measured in degrees. Now, because we've got the output is following the input, okay, there's a delay. That's called a lag. And that means that the angle that you get for the phase angle is negative, okay? So if there's a lag, the angle is negative. This would be a phase angle of minus 20 degrees or something like that. Okay, that's negative. So that's the basis of frequency response. This is what it looks like in the time domain. Well, how do we deal with this? How do we determine the various characteristics? Well, like I said, you can gain this data experimentally. If you've got a system, you plug in a frequency generator, okay, that will give you a range of frequencies, and you take the response of that system. But what about analytically? Well, you can determine frequency response from the open loop transfer function. Now, you remember when we did block diagrams last week, the open loop, if you've got a closed loop system, the open loop is G times H, okay? And this is what we're dealing with, open loop transfer function. Well, there's our input, R equals A sine omega t. Now, any sinusoid, we know from Euler's theorem, can be represented by A times e to the power of j omega t. Okay, that's Euler's. You should all be familiar with that, where j is obviously the square root of -1, the imaginary number. And any sinusoid can be represented with that, with the amplitude A. Now what we can do is take the first derivative of this term. Well, if you take the first derivative of r, okay, obviously in the s domain, that's going to be r times s. Yeah, any d by dt, you just replace with an s. But if we take the first derivative of this, obviously what you do is e to the power of something, you have to take the derivative of whatever it is to the power and bring that out. Okay, so we've got a j omega, so the j omega comes out here. Okay, and we said r equals a e j omega t. Well, we can replace this a j omega, that should be an e there, sorry, a e to the power of j omega t. And so s equals j omega. And so what you do is you take your transfer function in the s domain, and everywhere you see an s, you replace it with j omega. Okay? Everywhere you see an s, you replace with j omega. And this allows us to move from the s domain to the frequency domain. And we've got a frequency domain where the driving frequency is omega. Don't be scared by the complex number. It's nice and easy to deal with. So for a first order system, we know a first order system has this form, 1 over 1 plus tau s. This is the first order lag. Okay? And in the S domain, you've got the S in the denominator. And to get to the frequency domain, you replace that S with j omega. And so you end up with 1 plus 1 over, sorry, 1 over 1 plus j omega tau. For a second order system, we know that the standard form is something like this in the S domain. And what you do is you replace every occurrence of S with j omega. And so down here, obviously, that's going to be j squared omega squared. Well, we know that j squared is minus 1, hence the minus omega squared here. Okay. There was a S term in here, so that's replaced with j omega. And obviously that was just omega n, which is natural frequency. There's no S term in there. Now, beware with second order systems, this value and this value are different. Okay. This is the natural frequency, this is the driving frequency, and they are not generally the same. Okay. So let's consider a real example. Here's a transfer function, a nice second order transfer function, 5 over 2s squared plus 3s plus 1. And so we make, first off, we substitute everywhere we see an s, we put j omega in. Okay, and then you can do some manipulation. We know that the j omega squared turns into minus omega squared, and so that's minus 2 plus 3j omega plus 1. And so we can represent it like this. We can group together the things. Now, this is obviously a complex number, and it's nicer to deal with complex numbers if you can separate it into the real and imaginary part. Now, on the bottom, we've got this real plus j times an imaginary part, okay, but we want the whole thing to look like that. And so what we do is we see this complex number, you multiply the top and the bottom of this by its complex conjugate. Now, complex conjugate would be the real minus j times the imaginary, okay? We've got the plus, you multiply the top and bottom by the complex conjugate, and then we can separate out the fraction to be a real part and a complex part. So, that's what we had before on the previous slide. You multiply it by the complex conjugate. So like I said, we've got the denominator here, but with a minus sign instead of a plus. That's the conjugate. Obviously, 1 divided by that is 1, so we're not actually changing the value of the fraction. We're just multiplying it by 1. And then we go through the process. You can multiply things out. Okay. That term and that term are the same, but that's plus and that's minus, so they actually disappear. Okay. And obviously we've got a j 3 omega here and a minus j omega 3 here, so you can multiply them together to get minus 1, 9 omega squared. And so you end up with this down here. Again, we can make some simplifications, and you end up getting this. Now here we've got a real number minus j times the imaginary part, okay? So this is a real part and imaginary part. And that's a complex number, a minus or plus jb, okay? And so if we look at those separately, there's the real part, and there's the imaginary part, okay? So we've got, for this transfer function, which now in the frequency domain looks like this, you've got a real part and an imaginary part. Now, by knowing the values of these things, we can then work out things like the amplitude ratio and the phase, okay? And for that, we use complex number theory, okay? We know that the amplitude of a complex number is going to be the square root of the real part and the imaginary part, okay? This is if you imagine an Argand diagram, okay, with the imaginary axis vertical and the real axis horizontal, okay? And you've got your real number and your imaginary part, that produces a point on the diagram. Well, the amplitude is the distance from 0, from the origin, to that point. Okay? And since it forms a right-angled triangle, we can use Pythagoras' theorem to determine the amplitude of that complex number. And that gives us, for this system, the amplitude ratio. Now the phase angle, again, this is the angle that line makes, and that's going to be the tangent, because we're dealing with a right-angled triangle, It's going to be the inverse tangent of the imaginary number over the real number, and that will give us an angle of that line. Okay, so that will give us the phase angle. So we use the Pythagoras theorem to get the amplitude ratio, and then we just use trigonometry, the inverse tangent of the imaginary number over the real number, and you get your phase angle. And so with that system, okay, so the system looked like this, okay. What we do is we drive the system with a range of different frequencies. And then depending on the frequency, we'll get different values for the real and the imaginary part. And so what we can do, once you've got these equations, you can then use them to generate a table of results. And that looks something like this for that system. So I've got a range of frequencies down here. And here I've got the real number, the imaginary number, okay, and so I've got the amplitude ratio, and then I've got the phase angle. Okay, so I've used those two columns to generate this column and this column. Now notice my range of frequencies is not a linear scale. It's a sort of logarithmic scale. I've jumped up in different increments. And that's because as the frequency increases, the things take time to change. But we'll cover that in a second. So there's my table of responses. How can I draw this out? Well, there's a couple of methods that we're going to cover. The first is called the Nyquist diagram, and the second is called the Bode plot. Now, Nyquist diagram. The Nyquist diagram is essentially a polar plot on an Argand diagram. An Argand diagram is where you've got the horizontal axis is the real part, and the imaginary axis is the vertical axis is the imaginary part. Okay, and you plot those amplitudes and the phase angle on the diagram. And so how do we look like that? Amplitude is the radio coordinate, and then the phase is the angular coordinate. And so with our example, there was our transfer function in the frequency domain. There's the table of response. I've taken out the real and the imaginary parts here because all we want is the amplitude ratio and the phase. And that is the Nyquist diagram for that system. Okay? There's the origin, 0, 0. Okay? And we can look at that. If we take the first point, at 0.01 radians per second, okay, you can see the angle is minus 1.7 degrees, so we're virtually horizontal, and the amplitude is about 5, so we're out here. There's 4.5. 5 would be just beyond this point. So there's 5. Okay. Let's look at another one. Let's look at the one at minus 47 degrees. Okay. Well, that's 45 degrees. 47 is slightly further along. And we can see the amplitude is 4.1. So the distance from there to there is 4.1. And you keep increasing in frequency. Let's look at one further down. This is a frequency of 1 radian per second. And we can see that the amplitude is 1.58. Okay, so we're down here. And the angle is minus 110. So that angle there, that's 90. So that's going to be about, minus 108-ish. Okay. And like I said, you do that for a range of frequencies. And as you get closer and closer to infinity, you'll end up with an amplitude ratio of 0 and a phase of whatever. So that's a Nyquist diagram. Okay. And they're quite useful for dealing in terms of stability, but like I said, I'm not covering that this week. So that's one way of representing it. The other way of representing it is called a Bode plot, and this is what we're going to focus on. Essentially, a Bode plot is two logarithmic plots, okay, on a semi-log scale. You've got an amplitude ratio versus the frequency and the phase angle versus frequency. So you've got two graphs. One shows the amplitude ratio, one shows the phase angle. And an example, we'll take our example that we worked on before. Again, we take our values of the amplitude ratio and the phase angle, and we end up with two plots. Okay, we've got this represents our amplitude ratio, and this represents the phase angle. Now, notice that the amplitude ratio over here is actually measured in what's called decibels, and so we need to convert the amplitude ratio from that number to a logarithmic scale, and that's useful for a number of reasons. So if we take our amplitude ratio measured in decibels and you convert it using this, conversion. There's the amplitude ratio that we've calculated. You multiply it by 20 log amplitude ratio, okay, 20 log times the amplitude ratio to get the amplitude ratio in decibels. And logarithms are helpful because obviously straight lines can be, curves can be represented as straight lines, and then when you're multiplying things together, you can just add them, okay? And so, with that example, so that we've taken the amplitude ratio and the amplitude, you can convert from that to that, and that is what we've plotted. So we start out at about 14, and we come along, and then as the frequency increases on a logarithmic scale, notice why I did the logarithms there, okay, the amplitude ratio starts to drop. At this point it crosses 0, and then it starts to be negative, okay? Phase is measured in degrees, so we do the same thing. There's our table of results, frequency and phase angle, and then you can plot that, and we get this nice sort of S shape, which is a characteristic of a second order system, which is what that example was. So that's a Bode diagram, okay? What you do is you take the amplitude ratio, you do 20 log times the amplitude ratio, and you plot that on your Bode diagram. And for that you need a lin, log, or semi-log paper, which we will provide you in the tutorial sessions, okay? Because one of the tutorial questions asks you to plot, or in fact a couple of them ask you to plot Bode diagrams, okay? And so you need lin, log, paper, and then you just plot the points. You pick off those range of frequencies and you just plot them, and you draw a line connecting everything together. And the same with the phase diagram. You just take the same type of paper, you plot the phase like that as well. And you want to choose a range of frequencies that will suit your data. Now, when you're constructing a Bode plot, okay, the sections of the transfer function can be represented as straight lines or asymptotic approximations. So getting the table of results is one way of doing it. Okay, the other way of doing it is to look at the transfer function and look at what makes up that transfer function. Okay, and we can then draw a Bode plot from these what's called asymptotic approximations. And so, with this example, okay, I could have just looked at the transfer function and I could have drawn straight lines that are associated with that transfer function. And so that would automatically have given me what the thing is about to look, what it is, what it's going to look like, okay? And you'll end up with straight lines, and the only variation will be around the breakpoint, which is this point here, where there's an intersection of the straight lines, and you can see that that would be a slight variation. But outside of the breakpoints, you're going to get quite a close approximation. And so what we do is we break down the transfer function into its constituent parts. And every constituent part of a transfer function will have a certain type of frequency response. And so the building blocks for transfer functions, we know there's sometimes gains. You can sometimes get differentiators, which is an S in the numerator. You can get integrators, where there's a 1 over S term. You can get a first order lead term, which is a 1 plus tau S in the numerator, or a first order lag, which we've seen is 1 over 1 plus tau S. And you can gain an order. Second order lead has that form. Notice this is the same form as we had before, but I've divided by omega n squared to get 1 here, omega n squared on the bottom and omega n there. And a second order lag we've seen before looks like this. Okay? So that's 1 over that second order function. And each of these terms has a certain type of frequency response. Okay, so this enables us to look at a transfer function and then draw the Bode diagram without having to make a great big table of data. Okay, you can just draw it using these straight line approximations, and they've got a certain type of response. Now I'm going to go through what each of these looks like. Okay, but like I said, go to Blackboard. On Blackboard, there's a handout, and it lists all of this stuff. Okay, and so see the handout on Blackboard. For a gain, okay, the amplitude is a straight line. And that amplitude will depend upon your gain. And you do 20 log k, you get the value of that straight line. Okay, and the phase, there's no phase associated with the gain, so the phase is 0. With a differentiator, so this is the S term, we get a 20 dB per decade rise as the frequency goes up. Okay, and it will cross the 0 point at at 1 radian per second. Okay, this is what a differentiator looks like in the frequency domain. And the phase for a differentiator is plus 90 degrees. Okay, and a constant plus 90 degrees. An integrator, you can imagine, is a minus 20 dB per decade. We know what decade is, yeah? Every 10, multiple of 10, so this would be 1. The next decade would be 10. The next decade after that would be 100, and so on. Okay, well, minus 20 dB per decade is an integrator crossing at 1 radian per second. And this is plus 90. Well, an integrator is minus 90 degrees. Okay. Like I said, this is in your handouts on Blackboard. So, like I said, visit them, and you'll need them for the tutorial sessions. Okay, a first order lead. So this is the 1 plus Tor S. Okay, corner frequency. So basically, you start off at 0, and you reach a point related to the transfer function. Okay, sorry, the time constant. Okay. 1 over Tor, and after that point, the thing rises at 20 dB per decade. And the same case here, we've got you start off at 0. At 1 over Tor, you should be at 45 degrees, and then after that point, you should be at 90 degrees. And so this is at 1 over Tor, 1 decade before, you start moving away from 0, and 1 decade afterwards, you start leveling out at 90. A first order lag, so this is 1 over 1 plus Tor S, is the inverse of this. Okay, so again, you've got to start off at 0, you end up falling at minus 20 dB per decade. And your break point is 1 over Tor. And the same thing here, we go from 0 to minus 90. And lastly, there's our second order lead and second order lag. And here, instead of 1 over Tor, we've got omega n, okay, because that's related to this transfer function. And instead of it being plus 20, it's plus 40. And we go here from 0 to plus 180. Second order lag, we start at 0, at omega n is our break point, and we drop at minus 40 dB per decade. And we go from 0 to minus 180, as opposed to 0 to minus 90, which is with the first order system. And the true curve at the breakpoint depends on our damping ratio. Okay? If we've got a low damping ratio, you end up with a system that comes along and it peaks up and then drops back down again. Okay? And if you've got an overdamped system, you can end up with a system that looks a bit like a first order system. It just drops down. Like I said, if it feels like I'm going too fast, I probably am. I'm sorry about that, but we've got quite a lot to get through. But we'll go through an example of making a Bode diagram from a transfer function. And so let's do an example. Draw the Bode diagram for the following transfer function. Okay, so here's our transfer function. We've got a gain of 5. We've got a 1 over S term. There's our integrator. And we've got one first order lag and a second first order lag. 1 plus Tor S and 1 plus Tor S. Okay? And so sticking j omega in for every time you see an S, well, there's a j omega there, a j omega there, and a j omega there. When you're doing this, stop there. Okay? Because from this, we can then generate those various terms that will make up our Bode plot. Amplitude ratio. Well, you take each term, that one, that one, that one, and that one, and you do 20 log for each of those things. And so we've got 20 log 5, okay, and then these are minus because they're all on the bottom, 20 log omega, 20 log square root of 1 plus, you can see that's the amplitude ratio, yeah, Pythagoras' theorem. There's the real part, there's the imaginary part, 1 plus 0.2 omega, And then we've got 20 log 1 plus 0.05 omega squared. Okay. Here we've only got the imaginary part, and so you've got obviously omega squared, square rooted, so that's where the omega comes from. And so this is our amplitude ratio, okay? And in decibels, we've got each of these terms, and they all refer to a certain type of response. And then for the phase, well, phase, there's no imaginary part here, so the phase is 0, okay? Obviously, you've got a minus sign there because it's on the denominator, and we've got a j omega, and so you can work out the phase is going to be minus 90. Here we've got inverse tangent of 0.2 omega, and then we've got the tangent of 0.5 omega, because obviously this is the imaginary part, this is the real part, and when you've got 1 on the bottom, obviously it's just going to be that term, the inverse tangent of that term. So there's our terms that we're going to use to build our Bode plot. And we take each of those terms separately. And so for the first off, we'll start with that gain. 20 log 5 we know is 14 decibels. And so it's a straight line. We knew that a gain was going to be a straight line. And our amplitude ratio is 14. And we know that so that's with our gain. We know that at that point the phase is also 0. The second term we know is minus 20 log omega. Okay, so this is just an integrated term. It's minus 20 dB per decade, and it crosses omega at 1 radians per second. We then have our two first-order lags. We know that one first-order lag, we've got a breakpoint at 5 radians per second. Okay, and so before 5 radians per second, the slope is 0, and after 5 radians per second, the slope is minus 20 dB per decade. And we know it's 5 radians per second because you can take 1 over the tau, which we saw before, and you end up with 5. 1 over 0.2 is 5. And then you can do the same thing with that second first order lag. Breakpoint is at 20 radians per second, 1 over 0.05. Before 20, the phase is 0, so the amplitude ratio is 0, and after 20, we get minus 20 dB per decade. Now, because they're all logarithmic, okay, we can add them together, although in the transfer function they're all multiplied together. We have the gain, the integrator, and the two first-order lags. They're all multiplied together in the transfer function, but because these are all logarithms, you can just add them together to make up your complete system. And so we take each of the terms. Well, there's our gain. There's our our integrator. Then we've got one of the first-order lags with a breakpoint at 20, and the other one at a breakpoint of 5, R3. Okay, so R1, R2, R3, and R4, and you need to add all these together. And so what you do is you take the first two. Let's take R1 is there, and R2 is there. Now, notice that it should be crossing at 0, but when you add these together, obviously you're going to move this point up to there, aren't you? And so you draw a line at minus 20 dB per decade, but from that point, 0. Because obviously R1, that's a constant value, and you add that onto this point here. So the whole thing moves up, and you end up with a line that happens to pass through 5 radians per second at minus 20 dB per decade. So R1 plus R2 gives us the blue line. We then add R3. Okay, so that's minus 20 dB per decade. R3 we know came along at 0, and then at 5 radians per second was at minus 20 dB per decade. Well, minus 20 plus minus 20 is minus 40. And so you end up with minus 40 dB per decade up to 20 radians per second, because obviously R4 happened at 20 radians per second. So that's minus 40. And then above 20 radians per second, we've got the R4 coming into action. And that's another minus 20 dB per decade, because again, it's another first-order lag. Well, minus 40 plus minus 20 would be minus 60. And so we end up with that shape, minus 60 dB per decade. So there's the amplitude ratio. We'll come back to that in a second. The next up, we've got our phase to work out. Well, the phase, it is quite easy just to make a little table. There's our phase. That's what we came up before. The minus 90 minus tangent, inverse tangent of 0.2 omega. and minus the inverse tangent of 0.05 omega. And we know that that phase, the complete phase, is going to be phase 1, phase 2, and phase 3. And so we make a table. Omega, we've just come up with a bunch of numbers here that seem to match what we were looking at. Okay, omega 1, that's minus 90, that doesn't change. Omega 2, well, plugging in omegas in that equation will give us those values. And we've got omega 3, and you add them all together, and you get that number there. Okay, and this is what we plot on our diagram. And so if we took, there's our lin log paper, there's our amplitude ratio relating to that axis there, and then we've got the phase angle relating to this axis here. And so there is a Bode diagram using asymptotic approximations from the transfer function. Okay, all we did is converted it to j omegas, okay, and then we separated it out into its constituent parts. Okay, the constituent parts being a gain in this case, an integrator, a first order lag, and a second first order lag, and they relate to each of these things. The first line represents the gain and the integrator. This line is the first order lag. This is the second first order lag. And we said that with the gain, the phase is 0, but with an integrator, the phase starts at minus 90, so that's why we're at minus 100 already at this point. Okay, and it's a third order system, yeah? So we end up going from 100 to minus 270. So that's how we draw a Bode diagram. Like I said, go to the handout, it will come out, like I said, step by step. And in the take advantage of the tutorials, okay? If you're not going, now's the time to start going. Because like I said, at the beginning of this course, it is a tough course, and you will need the time in the tutorials to do this sort of stuff. And you do need to know this, okay? We can ask you to plot a Bode diagram of a transfer function in the exam, okay? And you need to know how to do this. Right, so that's how to construct a Bode diagram. Now we're going to go in the opposite direction, okay? We're going to be given a Bode diagram, and from that we need to work out the transfer function, okay? So this was taking the constituent parts of the transfer function, breaking it down, and plotting on the Bode diagram. Now we're going to look at the Bode diagram and go the other direction. And so you can use the Bode diagram to estimate your transfer function. So this is, like I said, this is the situation where you're given a real system, you plug in your frequency generator, and you range the frequencies from, say, 0 up to 100 hertz or whatever, however you want to vary the frequencies, and you get your data out, and that data can be then plotted on your Bode diagram, okay? And so you use the same rules before. Remember I went through what a gain looked like, what an integrator looked like, what a lag looked like, okay? And you use the same rules before, but you go the other way. And so probably the best way to do this is to look at an example. So I've been given some data, and I have to plot that on a Bode plot. That's step 1. Step 2 is you draw straight lines that fit that data, the amplitude data. And those straight lines will give you some clues about what the transfer function is going to look like. And then, those straight lines must be multiples of 20 dB per decade. So 0, plus or minus 20, plus or minus 40, plus or minus 60, etc. Okay? Due to the way that we've worked out amplitude ratio. 20 log the amplitude ratio. So they're going to be plus or minus 20 dB per decade. And approximations must pass through the data points at the lowest and highest frequencies. Like I said, at breakpoints there will be variations, okay? There'll be gaps. But at the lowest and highest frequencies, the data points will be pretty true to the asymptotic approximations. And then you use the relationships that we covered to determine the values for the transfer function. So let's have a go at an example. So here's my data. I've been given a table of data obtained from a frequency response test undertaken on some control system. Okay, so there's some frequencies I've been given in radians per second. I've got my amplitude ratio in decibels and my phase angle in degrees. Okay, so there's my data points. I take a Bode plot and I plot those points. Okay, so those are the points that I've got for my data. This is the amplitude, the red ones, the amplitude ratio, relating to that one, and the green are the phase relating to that axis. So there's my points. Okay, I can then think about the asymptotic approximations. Like I said, at the lowest frequencies and the highest frequencies, those approximations, those straight lines, must pass through the data points. So I take the first point, our lowest frequency, and we try 0 dB per decade. Well, that doesn't really fit with any of the other data points. Okay, so I get rid of that. What about minus 20? Well, that's pretty close. That's pretty good. I think that's probably worthwhile. 40, minus 40? No, that's definitely wrong. So we know that that's going to be minus 20. Okay, so that's the first asymptotic approximation. But obviously, at this point, these points don't line up whatsoever. And so there must be another asymptote that we can draw. So if we take the highest frequency and we draw minus 20, well, that doesn't really fit with this point here, does it? What about minus 40? No, that doesn't fit either. But we can go with minus 60, and we can see that that's pretty close. And notice with minus 60 dB per decade, well, basically, that's a scale in decibels. And so in 1 decade, this is some 200 hertz. 1 decade would be 20 hertz. Notice that minus 60 would be 60 on this scale. And we're down at, what, 72 there or something. And so minus 60 minus 72 is about minus 12, isn't it? And you can see that at this frequency, which is 1 decade down, we're about minus 12 on the scale. So that's how you get 60 dB per decade. It's a straight line. And if we draw a line between all of the points, okay, we get our line there. And we can see that the break point is at 20 radians per second, okay, which is the intersection there. And there's a gap between there and there of 6 decibels. And that gives us a clue about what the things look like as well. So there's our amplitude ratio from the data, and then there's our phase from the data. The phase, you just draw the points between the lines, and I'll talk about that in a minute, how that helps us. So there's our Bode plot from the data. Okay, so that's quite nice and simple. So first thing to look at, amplitude. Let's look at the slopes of those lines. Okay, a low frequency, we've got minus 20 dB per decade. High frequency, we have minus 60 dB per decade. Well, we know that a low frequency, we've got minus 20 dB per decade. Well, that must mean that there's an integrator in there. There's no straight line, so there may be a gain, but we don't know that yet. It starts off at minus 20. There must be an integrator in that system. And we know that because it goes from minus 20 to minus 60, we know that it must be a third-order system. Okay. So the low frequency, amplitude, and phase, 20 dB per decade, minus 20 dB per decade, and we know that the phase was minus 90. We saw. And that indicates that there is a integrator term. And like I said, our high frequency amplitude and phase, we've got minus 60 dB per decade, and the phase was tending to 270 degrees. And we know that that must mean that there is a third order system. There are 2 more S's that we need to find. The breakpoint, there was only one breakpoint. Okay, now breakpoints we saw was associated with first order and second order systems. Okay, there's one breakpoint, but it's going from minus 20 to minus 60. And so there must be 2 first order lags that are coincident with each other because there's only one breakpoint. A slope change of minus 40, that indicates there's an S squared somewhere. The breakpoint frequency is at 20 radians per second. And the difference between point of intersection and the true curve is minus 6 decibels. Well, we saw on your chart, you'll see that the difference between the point of intersection and the true curve for a first order lag was 3 decibels. And so with 6 decibels, that indicates that there must be 2 first order lags. And so we can see that there must be 2 coincident first order lags. There's a 1 plus Tor S term all squared. And that gives us our 3 S's on the bottom. So we know there's an integrator. We know it's a third order system, and we know that there's 2 coincident first order lags. And so our transfer function must look something like that. Okay, we've got a gain of k. There's our integrator, 1 over s, and then there's our first order lag squared. two of them together to get from that minus 20 to minus 60 dB per decade slopes. And so the transfer function terms, we know that breakpoint frequency, okay, we saw was 20 radians per second, and we know that's 1 over tau. Okay, and so you can say that tau is 1 over omega b breakpoint, 1 over 20 is 0.05 seconds. So there's our value for tau in here. Okay. And then to work out what k is, we have to look at the values. The integral term, like I said, crosses the zero line at 1 radian per second. Now, in this case, it didn't cross the zero line at 1 radian per second. If we go back to the picture, which we can do, almost there, we can see that it crossed the 0 point at about, what's that? 1, 2, 3, 4, 5 radians per second. Okay, so we can see that it crossed the breakpoint at 5 radians per second. And so the gain must have brought the integral term, which would normally cross here, up such that they cross 0 at 5 radians per second. And you can calculate how far up that is. That's about 14 decibels to get it to 5 radians per second. And so if we, I'm going to jump to the slide. Current slide. So integral term was supposed to cross at 1 radian per second. In this case, integral term crosses at 5 radians per second. And so the integrator is actually 14 decibels higher. Okay. And so to get that gain term, we've got an amplitude of 14 decibels. We want to go back to the amplitude in terms of, not in decibels. And so you say 20 log k is 14 decibels. Okay, so divide 14 by 20, you get 0.7. Okay, and then you anti-log 10 to the power of 0.7 gives us 5.01. And so our transfer function, you plug in those values, there's our transfer function. So from the data, using a Bode plot, we've gone from the data, which is just a list, a table of stuff, to what the transfer function for that system is. Okay? Which is an important thing. Say you're trying to design a controller for a system that didn't used to be controlled, okay? But you don't want to make a whole new system, okay? So you don't design it analytically, but you want to design a controller for it, okay? What you do is you take your system, you give it you generate a frequency, a range of different frequencies, and you generate a table of data. You plot that data on a Bode plot. You then go through the steps we've done to generate the transfer function. You can then plug your transfer function into your block diagram, design the controller so that that block diagram behaves the way you want it to, and bam, you've got a controller for that system without having to know anything about the system beforehand. Okay? This is the advantage of this sort of method. And this is called system identification. So we've gone through this stuff quite quickly. Like I said, you can download the slides on Blackboard, print them out, go through them in your own time. Simon is very kindly videoing the lecture. That will go up. It won't go up today, I'm afraid, because my computer's out of action, but maybe tomorrow, maybe Monday, okay? And we, like I said, we'll, these slides will be up there, and there's some supplementary slide notes as well. So, today's lecture, we introduce frequency response, frequency domain, conversing from the S domain to the frequency domain, frequency response, where you plug a sinusoid into your control system, into your transfer function, and you get a response, and that response will vary depending on the frequency of your input, okay, and it will vary in amplitude, and it will vary in phase lag, or phase lead. And so that will give us the values for amplitude ratio and phase. How do we determine them from the transfer function? Okay, and then they can be represented diagrammatically using either a Nyquist diagram or a Bode plot. And we can then go through and plot the frequency response. Okay, and this will produce the Bode diagram or the Nyquist diagram. System identification will go from a Bode plot to a Nyquist diagram back to your transfer function. Okay, that's it. Thank you very much, and I'll see you in the tutorials and next week.